Hi to all. Here we'll be discussing some numerical problem related to the induction motor starter, three-phase induction motor starter. Here one problem is given. Just read out it. 150 kilowatt, 415 volt, three-phase, 50 hertz squirrel cage induction motor has full load slip. Full load slip means when it will operate at full load speed, that time the slip will be what this much. Okay, its standstill impedance is 0.86 ohm per phase. This standstill impedance means whenever it will at block position, rotor is not rotating at that position, the impedance, per phase impedance is this one is phase, this one is phase, this one is phase. This is the stator of induction motor. Not this is auto transformer. Sorry, this is auto transformer, and it could be the motor induction. Okay, then the phase will be this, and if the maximum allowable current, supply current at the time of starting is 100 means at the starting maximum 100 ampere current can flows we can allow. Okay, calculate the tap position at the and the ratio of starting torque to the full load torque. As in at full load working full load at 0.85 lagging power factor is working. So now here the question is given the tapping position is simply, if tapping position is given, simply we have to consider that this kind of starter will be three-phase auto transformer starter. Okay, now here simply we just have one figure as three-phase supply is given, and this is the auto transformer. This winding will be giving the supply, and this is the variable point. From the variable point we will be getting three-phase supply. Okay, now how much? Suppose here 415 volt. So the 415 volt this side we will be getting, and at that starting how much voltage we don't know. How much voltage? If we know that voltage, suppose some voltage is there, V dash. From there, then we can simply calculate the tappings. V dash divided by 415. That we can simply calculate. Okay. Otherwise, this line to line voltage also we can calculate the phase voltage. If it is star connected, then will be obviously phase voltage will be there. Clear? Now the problem is what we'll be discussing. The problem is we have to find firstly the full load current. So what would be the full load current? Full load current will be how much? Full load current will be 415 volt. Sorry, how much? 50 watt. 50 kilowatt root 3 times into voltage 415, and power factor is 0.8. This, as you know, this how will be getting root 3 times current EL cos phi is simply that 50 watt, 50 kilowatt. From this equation we will be getting the full load current. So full load current is how much? 50 into 1000 root 3 into 4 81.85, it's like 18 point something, 81.83, it is 81.83. This much current. This is the full load current. Now simply we have to see the short circuit current. Short circuit current how much? Short circuit current how much means that under standstill condition, how much will be the short circuit current? Okay. So short circuit current will be, for this, how much? What is given? One condition is given, boundary condition. Its standstill impedance is 0.867 per phase. Okay. Per phase voltage is this much. Okay. So firstly we have to see the per phase voltage. So per phase voltage how much? Per phase voltage is 450 volt divided by root 3. So how much will be? It will be around 240 6 volt. Clear? Now the current. So short circuit current will be ISC .6 divided by how much? 0.867 divided by 0.867 6.67 ampere. Okay. Now as you know that for the auto transformer starter, if the tappings k times of this voltage V dash, the supply voltage, suppose k times of a voltage we are applying at starting instant. Okay. So then how much will be the starting current? Starting current, we know that starting current is k square times IS for auto transformer starter. Okay. 1 k times is for voltage reduction and 1 k times for the auto transformer. Clear? Now what will be the K? What will be the K? K is nothing but will be the IST and ISC. Clear? But here starting current, the limiting current is given how much? Starting limiting current is given 100 ampere. Okay. So how much will be the K? K will be the 100 under root 100 divided by 276. It will be 0.660. That means 60.1%. Okay. So that means what? So it means if 415 volt is supply voltage, then at starting how much voltage? it will be 259 point something voltage at starting voltage across the motor you can apply. Okay, so this is the phenomena of auto transformer starter. But actually what we need to find one more. So see the question. Question is there to give the maximum allowable current 100 ampere. Calculate the tap position. Tap position will be at 60%, and the ratio of the starting torque to the full load torque. Okay, so what would be the ratio? Starting torque and load torque. What would be the ratio? You know that this is the square times of ISC so it will be the full load current square into times of full load slip. We have seen this expression through in the study of the auto transformer. Okay, so now, and also you can see the link in the description. Okay, for the auto transformer study. Okay, starting of auto transformer study. Okay, now what we know, this K is 0.6 square, and ISC and IFL how much? ISC how much? 276, and IFL how much? There it is how much got? IFL full load current how much we got? Full load current is 81.83. 81.81 square into how much slip was? Slip was 4%. Full load slip of 0.04. So it would be numerical value 7681.83 square into 0.6 square into 0.04. So it would be 0.1.63 times of torque. So that means it is like this. Suppose it is full load torque with the starting torque 0.6. So if it is full load torque, then it will be the starting torque. Starting torque in case of auto transformer is the 0.6. But here, when it will full load torque, we know that it will be run directly to the supply. There will be no auto transformer. So it will be running condition. Okay. So here is one question solved. Okay. If there any doubt, you can directly ask me. You can comment. You can directly contact me. Okay. So this is the one question related to the auto transformer starter. Okay. So and one more question we'll discuss. The question is the A 3-phase squirrel cage induction motor has a starting current of 6 times of the full load current. Starting current starting current, how much? Starting means that is short circuit current. Okay, starting. See one thing. At starting means what? If inertia is there, if motor inertia is there, exists, then at starting instant, the motor is what? Stand still. If motor is stand still, means that is at nothing but the short circuit condition or block rotor condition. Blocked rotor condition. Totally blocked. Okay. That means what? That would be the short circuit current. So short circuit current is given as a 6 times the full load current. 6 times of full load current, and also given the full load slip. Full load current at slip has a starting current of 6 times that the full load current at slip, and full load slip is how much? 0.05. Obviously the starting slip will be at starting. Slip will be is equal to 1. Starting slip. Okay. Now what is given? That we have to calculate the line current and the starting torque in per unit values of full load values. With respect to full load, we have to find this line current and starting torque. Okay. Firstly, for direct switching. Direct switching, what? If there is no switch, starting means available, neither resistance starter, neither or delta starter, neither auto transformer starter. So what would be the starting current? So for direct switching, how much? The starting current will be 6 times of full load current. Clear? So what would be the per unit value? Per unit value would be the, with respect to full load current, will be 6 per unit. Okay. Now the torque. Now the starting torque. What would be the starting torque? Starting torque and full load torque. What is the proportionality ratio? The ISC and IFL square into ISF. So this much. Okay. Now what is this value? This is the 36 IFS square divided by IFS square, cancel out, and SF is 0.04. How much was given the slip? One time slip is given 0.045. Okay, so slip is 0.05. So how much? 36 into 0.05 is 1.8 times. 1.8 times. It's how much? 1.8 times of full load torque. Okay. So starting torque is 1.8 times of full load torque. Okay. So how we can explain this with the diagram. See, it is the torque speed characteristics. If it is torque speed characteristics. Okay. If somewhere we find this operating point, full load operating point at full load. So obviously this torque will be the full load torque and this would be the starting torque. Okay, almost double if it is full load torque and it will be starting torque. Full load starting torque is 1.8 times of full load torque. So obviously this point would be higher position from this point. Okay, so this point is operating point at full load. Okay, and this will be the starting point of the full load starting point. Okay, if direct switching for direct switching or direct switching for direct switching. Now we'll go for the auto start delta starter. So what would be the start delta starter in case of for second case? Star delta starter. As we know the what working function of start delta starter. You go. I explained the start delta starter, so you can follow that lecture to gain the knowledge of first start delta starter. Then you go for the solution. Okay, first go for the study about this starter, and then we come with this solution. Okay, so starting current, as we discussed the starting current. So now just simply I want to discuss the start delta starter. Whenever the starter is in start connection, starter will be then starting current will be the short circuit current of 2-3 times this much starting current will be when we are using as delta starter. But if the machine is running condition, machine is working as delta connection. So delta is there will be the starting current. How much? Starting current will be short circuit current 2-3 times of short circuit current, this much. Okay, so now what would be the switching ratio, is current ratio with respect to delta? With respect to the switching ratio of delta, suppose star connection starting and delta connection starting. So how much in case of star connection? How much? ISC 3 times and here 3 times into ISC. So ultimately how much will be the 1-3 times 1-3 times. So this starting current in case of delta means it is nothing but the starting current of direct switching. In case of direct switching, because see, direct switching means what? We are directly switching to a delta connection, not we are using star connection. Okay, we are not using star connection. At that time we will be directly switching delta. So if we directly switching delta, then current will be that much on short circuit current. Okay, clear? So this much will be the starting current. How much will be? So starting current will be 1/3 times of direct switching current or delta connection. So 1/3 into how much? This direct switching current, how much? 6 times of full load current. So this will be the 2 times of the load current. So that means 2 per unit. 2 per unit. Okay. Now the starting torque. So the torque will be how much? The starting torque in case of star. Okay. Starting torque in case of delta. Okay. So we know the proportionally voltage proportional. So how much? So ISC to 3 times square. That is 3 ISC. ISC. So this is one part. So this much. So ISC into ISFL, how much? ISC and ISFL 50 millivolts. There is 6 times 4. So 1 by 8. Five. This much. No. 6 times. So 6 square into 0.05 divided by 3. So 6. So the power will be 6 with the ratio of starting torque. And so if you compare with this for delta switching and for this switching, so this is what it is. So it was for direct switching. This considered the starting torque for direct switching. Now for this 4.6 times 4. So if it is 1, so it would be like this. Star delta 30. So here in simplicity this starting torque is reducing and here starting torque is that much. So in case of starting torque, so you have to be careful about this. The starting torque anyhow for star delta starter, it's mass reduction. So if the load is already connected, so we have to take care of that. We will able to overcome that load torque at starting moment or not. Okay. Otherwise motor will not start. Okay. Clear? Suppose we are simply giving this type of load. Suppose characteristics, this is the load characteristics. Okay. So for this load, if it is already connected, so we can't overcome. We can't start the starting. because load torque is greater than the starting torque for delta starter. So we have to, if this load is there, so we have to just simply reduce. Then we simply, if it is run and it gets in running condition, then you can apply as load. Okay, so it will be the solution. Okay, but in case of direct switching, it will start basically, because this starting torque for delta switching, the starting torque for this load torque fashion is greater, much more greater, so it will start. Okay, okay, thank you for listening. Okay, we'll come again with one in the next video. We'll come with one more solution.